So who could tell me where we left off last class? Was it a specific example that we were doing?
One-sided limit.
One-sided limit. Did I just start defining it? Or did we start doing one-sided limits?
We just defined it.
We just defined it, right? Okay. So if you have the limit as x approaches b of some f of x, if this equals L, notice that that implies that the limit as x approaches b from the left of f of x equals L, and that the limit as x approaches b from the right of f of x simultaneously also equals L. Now recall that the limit as x approaches b from the left is the same thing as evaluating function b minus omega, and it rendering the result L. And over here, it's the same thing as the function b plus, evaluating b plus omega, and it rendering the value L. So let's do some examples. What about the limit as x approaches 3 of this? Have we done this before? Did we do this example yet?
Yeah, that's what we did. We said it doesn't exist.
Right, okay. So we did do this one. Okay. So let's do another one then. Let's say 1 of negative 3 over . Let's say it's the limit as x approaches 1 of negative 3 divided by the quantity x minus 1 squared. Okay. Let's evaluate the function at 1 and see what happens. So it's undefined when we evaluate it at that value. But let's calculate the left-handed and right-handed limits. So let's approach the function from, let's approach 1 from the left. Notice that this is the same thing as 1 minus omega n for every x you see. Because over here, the limit as x approaches b from the left is like evaluating f of x at b minus omega. And the function approaching b from the right is like evaluating the function b plus omega. So we're approaching 1 from the left. So we're going to evaluate our f of x at 1 minus omega. And let's see what happens. And I dropped this negative here. So the ones cancel over here. Negative 1 and 1 cancels. So we're left with a negative omega squared in the denominator. When we square it, it becomes positive. And notice that this becomes a negative 3 capital omega squared, which will render what? The real result what? Correct. All right. Correct. Now let's take the limit as x approaches 1 from the right. So then we'll get negative 3 of your f of x. That's equal to your f of 1 plus omega. It's a negative 3 all over 1 plus omega minus 1 quantity squared. So the ones cancel again. And you're left with a negative 3 over omega squared, which is the same as negative 3 capital omega squared, which renders the real result correct. So the left hand and the right hand limits agree, right? So we can say that this thing right here is equal to negative infinity. It's the value in which the left hand and the right hand limits agree. The total limit equals infinity, negative infinity. The total limit. What does that mean about what the graph looks like? Well, at 1, the function is going to have a vertical asymptote. And the function will dip towards negative infinity from the left and the right as it approaches the value 1 on the x-axis. So this is our f of x in yellow. Okay, that's about it for this section. I knew we were very close to finishing it. So that was section 1.4. Moving on to section 1.5. Moving on to 1.5 here. All right. This is called limits part 2. More on limits. So let's define this piecewise defined function. Let's say f of x is defined in pieces. We chop up its domain and we say the function should equal 2x for values of x less than or equal to 0. And we say that the function equals 4x for values of x greater than 0. And we wish to calculate what is the limit as x approaches negative 3 of f of x. So we continue to calculate the left and the right hand limits. So the limit as x approaches negative 3 from the left of f of x. The same thing as evaluating f of negative 3 minus an omega. But this function changes, right? Right now, we're slightly to the left of negative 3. Which one of these should we pick? Yes, why?
Because negative 3 is less than.
Yes, yeah. So the part of the piecewise defined functions domain that activates this 2x is where we're at. So we have to evaluate the function at that 2x, namely 2 negative 3 minus omega. We evaluate it at that. So this becomes negative 6 minus 2 omega, which renders the real result what? Very good. Now let's evaluate the right-handed limit. What is x approaching 3 from the right of f of x? Well, that's the same thing as f of negative 3 plus an omega. But now we evaluate it here, right? Because this is greater than 0, values greater than 0. Is that true? No, actually, we're still evaluating it here because even though we add an omega, it's still negative. So again, we have to use the 2x. All right? And this renders the real result what? Yes. So the left hand and the right hand limits agree. And so we know what the limit equals. It equals negative 6. As x approaches negative 3. Okay. Let's do another one. Let's define our piecewise defined function. It equals x sometimes and x squared sometimes. Let's say when those times are. Well, let's say it equals x when the inputs x are less than or equal to 0. And then it equals x squared when they're greater than 0. So if you graph f of x is going to look like this. It's going to look like a line with slope 1 for negative values. And boom, at the origin, it shifts into a parabola. This would be your f of x in yellow. We wish to calculate what is the limit as x approaches 0, because that's when that interesting stuff is going on. We have to calculate the left hand and right hand limits. So this approaches 0 from the left of f of x to the left of 0. We pick this one because this is a set of values of x that are the inputs that are left of 0 or at 0. So that's like evaluating the function 0, the left-handed limit minus an omega. But then our function is just x, so this becomes 0 minus an omega, and that's all it is. And 0 goes away, so this becomes minus omega, which renders the real result what? Very good. Now, the limit as x approaches 0 from the right of f of x. The same thing as evaluating the function 0 plus an omega. So for values, so that 0 plus omega is slightly bigger than 0, all right? So it's going to activate this one. So now it's going to be 0 plus an omega quantity squared, which is the same thing as just an omega squared, which renders the real result what? Yeah. So the left hand and the right hand limits agree that the total limit is equal to 0. Right there. When you approach it from the right, the function's value is 0. When you approach it from the left, the function's value is 0. Let's get even more interesting. Let's chop up our piecewise defined function into 3 pieces. If I erase too early and you haven't written it down, don't forget that there's the lecture videos. You can always watch the videos and see if anything I erase. That's why I don't feel bad about erasing stuff real fast, because of recordings. If it wasn't for that technology, I would wait, make sure everybody's written it down and whatnot. One of the silver linings of this situation is I don't have to do that. So we want to know what is the limit as x approaches 2 of this function, this piecewise defined function. All right. So let's kind of get an intuition for what does the function look like. Well, something happens at 2. Something's going on at 2. So let's indicate here's 2. So for values less than 2, the function becomes a line with slope 1 and y-intercept 1. So at 2 and to the left, it becomes a line of slope 1, y-intercept 1. Well, if its y-intercept is 1, then we should have it going through its y-intercept, and we should have it having a slope 1. But it's not defined at this point right here. At 2, it's not defined. Notice that if it was defined, f of 2 would give me, or f of 2 would give me 2 plus 1, which is 3. So hence why I've drawn it like that. But we put a hole there because this is not defined at 2. We were just pretending that it was to kind of see where the height should be, but it's not. That's why we put a hole. If it was, we fill in this hole. But we're not going to because that's not what the function is at that point. At 2, it becomes the value 11. So at 2, it turns into 11. So we get a dot up here at height 11. And at values beyond 2, it becomes a parabola. So for 3 and for 4, it assumes the value 3 squared, which is 9. Let's say 9 is right here. And 4 is 16, so it will be up here. Maybe a little higher. And so we can see that, oh, from here on out, it's also not defined at 2. So there's the hole, but then right past the hole, we can continue to function like so. So this yellow is our f of x. We're interested in seeing what is the limit as x approaches 2. What is the function doing? Is it going to equal 11? Or is it going to equal something down here? Let's see. Clearly, f of 2 is 11 because it's defined to be that way. But let's see what is the limit when you approach 2 from the left of f of x. That's the same thing as 2 minus an omega, or f of that. So for values to the left of 2, we got to pick this x plus 1. So f of 2 minus omega of that is 2 minus omega plus a 1. This becomes 3 minus an omega, which then is the real result. 3. What is the limit as x approaches 2 from the right of f of x? Same thing as evaluating the function at 2 plus an omega. But for values slightly to the right of 2, we activate this one, the quadratic expression. So we get 4 plus 4 omega plus omega squared, which renders the real result. Yes. So what's going on here? What is the limit? What is the limit as x approaches 2 of f of x? Do the left hand and right hand limits agree? So then, oh, it does not exist, right? The total limit does not exist because the left hand and the right hand limits don't agree. Because they don't agree, the limit can't exist. Trying to trick me, dude? Trying to trick me? So the limit as x approaches 2 of f of x does not exist because the left hand and right hand limits do not agree. So a function can be defined at a point, but it doesn't necessarily mean that its limit will be defined at that point. Let me redraw this because I kind of draw it wrong. We had the 2 was the function f of x. X plus 1 for values of x less than 0. Becomes 11 for values of x equal, or yeah, this is the 2 equaling 2, and x squared for values of x greater than 2. We had, okay, So here's one, y-intercept of that, it intercepts here, and it goes up till 2, it doesn't include it. So this part was correct. What was incorrect was I had the parabola coming out of here. It doesn't come out of there. Notice the parabola at 2, if we were to put 2 into here, it's 2 squared, which is 4. So here's 1, 2, 3, 4. So there would have been a jump right here. And then it goes on being a parabola. So that's why the left hand, the limit, as x approached 2 from the left, it ended up equaling 2. But at the limit, as x approached 2 from the right of f of x, remember it ended up equaling 4. This is why, because as you approach 2 from the left, the y value it assumes without touching 2 is 2. If you approach the value from the right, if you approach 2 from the right, the y value it assumes is 4 without touching 2. So this is what you would call a jump discontinuity. The left hand and the right hand limits do not agree. And don't forget that there was that one part of the function up here where we define what is it at 2. We define it to be 11.
So that's how it should look like.
Yeah, this is how it should have looked like. Yeah. I had these two connected and they're not connected. I drew it wrong the first time. Okay, so this is why the left hand and the right hand limits don't have the same value. The way I had it was, I had it coming through here. I had it like this, remember? If I had it like this, the left hand and the right hand limits would have agreed to equal 2. But I didn't do the function properly. If I plug in a 2 here, it outputs a 4. So it shouldn't start here, it should start here and become a parabola.
But that line should be on the 2, like on the y2 or y3. No, I'm talking about.
No.
Like, because you know that one that's going up?
Which one? This one?
No, the other one.
This one?
That one?
Yeah.
Is that like pole supposed to be on like y equals 2 or on y equals 3? Because you know
that whole. Oh yes, again, yeah, you caught another issue. It's supposed to be at x equals 2, where if you plug that into the function, that's 2 plus 1, which is 3. So you're absolutely right that this should be up here actually. But they're still not touching.
Okay.
Yes, yes, yes. Is that your question?
Yeah, yeah, yeah.
Yes, yes, yes. It should be up there, but they're still not touching. Yes, good catch. It's important to, you don't have to graph these to calculate these limits. It's not needed. But if you do graph them, you can check your results.
Is there questions like, can you like draw this graph?
Yes.
Yeah.
Yes, there will be. Yes, there will be. This problem didn't require it, but it helps to elucidate what's going on here. It shows you why the limits don't agree in value. Wait a minute. So for here, is that what we had? The limit approaches 2 from the left.
We have 3.
Yeah.
We got 3, didn't we?
Yeah.
That's why this should be a 3, not a 2. Good, good, good. Now everything makes sense. Good, good, good. Very good. I was gonna say, that should equal 3, because good. As you approach x from the left, the value of the limit equals what is the height on the y. Infinitely approaching it, it equals 3. But then coming from the right, infinitely approaching it, it becomes 4. So this is good that we get our left hand and our right hand limits like so. What I'm trying to say is we discovered this algebraically. You could also discover it visually. They're both the same thing, but sometimes you don't have the graph. You should do it both ways. You need to be proficient in doing it both ways, not just one way. Let's do another one. Okay, let's define our piecewise defined function. As x for values of x greater than 1, and as x plus 2 for values of x less than or equal to 1. We want to determine what is the limit as x approaches 1 of f of x. Okay. First, I'm just going to do it algebraically. Then we can graph it and see what's going on. Okay. Left-hand limit as x approaches 1 from the left of f of x. The same thing as evaluating the function at 1 minus an omega. Values slightly to the left of 1, not greater than 1, but slightly to the left of 1, evaluate like x plus 2. So this becomes an f of 1 minus omega 2. So then these add, and we get a 3 minus an omega, which renders the real result 3. Limit as x approaches 1 from the right of f of x is the same thing as evaluating the function at 1 plus an omega, which then values slightly to the left of 1, which when we add an omega to 1, it becomes slightly greater than 1. We just pick x. So this becomes 1 plus omega, which renders the real result 1. Notice that the left hand and right hand limits don't agree, so this limit does not exist. So now let's graph it. Let's see graphically what's going on. Okay, so all the action is occurring at 1. So for values less than or equal to 1, we have x plus 2. That is a line with slope 1 and y-intercept 2. So we know it's going to intercept the y-axis at 2. Okay, it has a positive slope. So what is it at 1? At 1, it's f of 1, which is 1 plus 2, which is 3. And guess what? Do we put a hole here or do we put a solid? Who can tell me why I'm doing that? Oh, and that actually needs to be at 3, right? Uh-huh. I'm repeating the same stuff, but I caught myself this time. But this solid part, why is it a solid? I'm just going to go through 2.
There's no, like, I think because there's no way it can be undefined.
Say what?
I don't think there's, like, it doesn't say that it should be undefined, is it?
Saying or equal to.
Yeah.
Piecewise.
Aha! This or equal to part is why it's a solid. If it was less than, but not equal to, it'd have to be a whole. But because it's less than or equal to, the function actually ends up being a solid point up there at 1, because we can evaluate it at 1. We don't even have to pretend. We can evaluate it at 1. F of 1 here would be 1 plus 2, which is 3. That's why at 1, we go up to 3 and we put a solid. We don't put a hole. Moving on, though, at values greater than 1, it becomes the line of y-intercept 0, slope 1. So at 1, which it can't be, but at 1 it would have been 1. Yes. See that? If it was defined, it would go through the x-axis over here for those values, because it has a y-intercept 0. But it's not. Okay, it's only defined for these values and on. Notice that our limit as we approach the function from the left at 1, we got what? 3. But when we approach the function at positive 1 and we come at it from the right, we get the value 1. You see what's going on there? I could have changed the problem here. Look, I could have changed the problem here and gotten rid of this completely. What would have that done? Would have made a hole here. What else? What else would it have changed? would have changed the left-handed limit?
No.
No, it wouldn't. Because the limit doesn't care whether it's defined at this point or not. It just cares what is it really close to it to the left. That's all it cares about. It doesn't care whether it's defined at that point or not. That is the point. No pun intended. That is the point of the limit. It's to discover information about functions without having to evaluate them at points in the function where the function might not be defined, or it's dividing by 0, or other kinds of misbehaving, mischievous function actions. As human beings, we want to be able to extract information out of the functions, because functions can represent a myriad of properties like electric field strength, flow rate of water, energy of battery. We can create functions for all kinds of things. The amount of fuel in a rocket as it starts to go off into space, it has a function that models how fast the fuel empties. It's a differential equation. And learning calculus will allow you to move on into differential equations. I want all of you guys to major in math. Well, what is your major?
Biochem.
Biochem. What is your major?
Computer science.
Computer science. Computer science?
Yeah.
And
Engineering.
engineering? Okay. Keep all your majors the way it is, but add a double major in math. Do it. Do it. Do it. Do it. All right. So let's say we have a function here. And let me draw this one carefully. We got a -4, -3, -2, -1, 1, 2, 3, 4, 1, 2, -1, -2, 5 here for good measure. The function does something like this. And then it goes through that -2. And it comes down here to -1. Solid, or -2. Solid, and then it goes, jumps here to 0, or to -1. Open, and then there's a asymptote, vertical asymptote here. And the function goes up like that. And then it comes up like this, and it goes through here. So our function's in yellow, f of x. Let's calculate some quantities with regards to this function. What is the limit as x approaches 2 of f of x? Now we're going to do them visually. Okay, so visually, what is the limit as x approaches 2 of f of x? See why you're quiet, because maybe I need to draw this part a little bit better, just a little bit better, so you can actually determine something. We want it to 1, so I'm going to draw it like so. So just a minor change. I just kind of changed how it rises up to allow you to see what is the limit as x approaches 2. From the left, it's like right here. From the right, it's like right here. What is this approximately at?
1.
Yes. So what can we say here? From the left and the right, it's approximately 1. This is visually seeing it. Okay. What is the limit as x approaches 4? Function. Yeah, you can kind of eyeball that to be -2. What is the limit? Approaches 6 of f of x. So the 6 right here.
I said 2, but it's 1.5.
Yeah, like 1.5, right? Okay. What about a -1? Or a -2? Yeah. Now, what about a -1? Yeah. What about y? Y. What is the left? Positive or negative?
Positive.
And then what is the right? Very good. So what would be the limit as x approaches -3? Well, what is f of -3? Doesn't exist. It's not defined at -3. What is f of -1? Or what is f of yeah? What is f of 1? Yes. F of 1 is -2. Because over here, if we come at 1, the function is outputting a solid at -2. But what is the limit when x approaches 1 from the right of f of x? Yes. And what is the limit as x approaches 1 from the left of f of x? Yes. You guys are getting the hang of this now. Guys see what's happening? So this was a purely visual exhibition of the concept of a limit. Okay. Now, let's give you some limit information and have you kind of construct a general graph that would satisfy at least that information. Okay. I had to deal with the Zoom thing because I feel like someone accidentally unmuted. Okay. So, some interesting stuff is going on at 4. So we'll put 4 there, and it's 0. So at 0, the limit is negative infinity. What should our graph look like? Well, it's going to have an asymptote there, right? And the left hand and the right hand limits had to agree for this to happen. So they're both headed down towards negative infinity. Now, f of 4 is 2. So we know at least at 4 is defined to be 2. We'll put a solid up there. Now, but it says that the limit as x approaches 4 is 1. How are we going to draw this? Well, you do it like so. You say, oh, the function must have left hand and right hand limits agreeing to be 1 at 4. But the function, when you evaluate it at 4 exactly, it outputs a 2. But its left hand and its right hand limits at 4 output a 1. So that's why we put a hole there and have the left hand and right hand limits seem like they're equal to 1. Drop this down a little bit more. There you go. So you guys should be able to be given some information and construct a graph that would uphold that information. Limits that are infinite would create asymptotes. Limits that have a value that's different than the value in which the function evaluates to would create a hole with some solid dot somewhere where it's actually what it equals. Okay, now let's do numerical estimates. Let's say we want to numerically estimate the value of the limit as x approaches 0 from the right of the square root of x squared plus 16 minus 4, everything divided by x squared. What does this equal? Well, you got to create an f of x table. And since we're approaching the function from the right, we pick values that are positive and are constantly approaching our function. See, these numbers are getting smaller and smaller and smaller positive numbers, which means they're approaching 0 from the right. So here at 0.1, when you evaluate f of x, which f of x is this, you put a 0.1 here, 0.1 here, see what the function cranks out. It equals 0.1249805. Then you move on, it equals 0.1249998. Then for this one, it's 0.1250000. You move on, you move on, you move on. What does the function seem to approach? What does it seem like the right-handed limit is? Yeah, 0.125. In terms of a fraction, what is 0.125? Is it 1/8? Maybe. So if you divide 1 by 8, you get 0.125. Let me do it real quick. Yeah, you do. So take a look. This algebraically would mean we evaluate this function. And 0 plus omega is just like an omega. But notice if we approximate what's inside the radical upstairs, to be just 16, we violate the approximation principle, right? Yeah, because then the top will be a 0. Because if this is just 16, square root of 16 is 4. 4 minus 4 is 0. That's not good. So what we do is multiply top and bottom by the conjugate. Moving the calculation over here, what you end up getting is a omega squared plus a 16 plus a negative 16, because negative 4 times positive 4. And then over here you get omega squared times the quantity, square root of omega squared plus 16 plus a 4. Notice that these quantities cancel, so you get an omega squared times the square root of omega squared plus 16 minus, or plus a 4 over here. So we're talking about numerical estimates, but right now we're algebraically doing it. We already estimated it numerically. So then we cancel these out, and we end up getting a 1 divided by square root of omega squared plus 16 plus 4. Now we can do some approximations here. Notice that we can approximate what's inside the radical to be 16, and then you get square root of 16, 1 over 4 plus a 4 over 8, which is the same thing as 0.125. Isn't that cool? So what we're doing here numerically and what we're doing here algebraically are the same thing. Sometimes doing this algebraic process is very difficult, and Sometimes it's so difficult that humanity doesn't know how to pull it off yet. There's certain problems that human beings don't know how to do fully algebraically, or what we call analytically. So we have to move on and do it in a numerical approximation method like so. That's why doing numerical estimates is valuable, and it has a lot of real world applications. Okay. Let's see here. Yeah, so we're about like halfway through this section here. So the section we have completed is 1.5. So I'll assign the homework for 1.5, but 1.6 is not completed yet, but feel free to start studying that section. We're in 1.6 right now. So once we complete 1.8, you'll have your first exam.
What day are we putting the homework for?